So, hi guys, this is Dr. Edwards again. I want to give some pointers now about the one dimension of delta function, and this should help with the homework problems that I've already given. So let me get started. This function is somewhat odd compared to regular continuous functions that you are often seeing in physics classes. The function then, so you can visualize it, is the following. It is a function, we call it delta. Lowercase delta is the standard. The function is equal to 0, except at the origin. So when x does not equal 0 anywhere, from negative infinity to positive infinity along the abscissa axis, the x-axis here, the function is 0 per unit length. And at the origin, in this case, the function goes to infinity. That's at one part. So that's the oddness. The function is flat right on the origin. Flat right on the x-axis when x doesn't equal to 0, both negative and positive. But right at the 0, it suddenly goes to infinity. Not only that, the integral of the delta function has a finite value. The integral of it, in this case, is 1. It's a unitless quantity. So if delta x has units of meters, if dx has the units of meters, then delta x has the units of inverse meters. He makes that comment here. Notice that the dimension of delta x are over the dimension of its argument, and x is the argument here. Okay, so it's inverse meters. Now you will often have a case where the delta function is not comparing x to the origin, but comparing x to some other finite quantity a. So as opposed to the function being 0 at x equals 0, I'm sorry, as opposed to the delta function being infinite at x equals 0 as it is in this case, here is equal to infinity at x equals a. How do we represent this aspect of the delta function? That comes up next. And we go on here. And so let me go on to this statement that is important. So since the delta function relative to the origin is 0 everywhere except at the origin, any function, any regular Riemann function times the delta function, you can go on and put at f equals 0, f at x equals 0 times the delta function, because it is 0 everywhere. So you may as well make that this is true. And if that's the case, then if that is the case, then the integral of some function f of x times delta x, the dx, is equal to, you can factor out f of 0 because it's a constant, then the integral from negative infinity to positive infinity delta x. Then you get that the result is the function, this function evaluated at f equals to 0 in this case. That is interesting. So here we have the product of a function, regular function f of x, times the special function delta x. And the result of that integral from negative infinity to positive infinity will always be some finite value. And here it is the value at f equals to 0. Why f at 0? And I'm going to explain that in just a moment. So what the author is showing here is that we tend to want to think of the delta function as a distribution, continuously getting smaller and smaller towards the finite position x equals 0. And when it does that, it goes to infinity. All right, let me go on. So now this is the way then that I want to think about this. So this is a function here, delta of x minus a. This is the standard way that you see it. So as opposed to the function being 0 everywhere except at the origin, now it's 0 everywhere except x equals to a. So it's only at x equals a that suddenly it's a hugely large function, infinite as we say. And the integral then will have some finite value if a is within the range of integration. Let me go there and show that to you. So here then. So as opposed to delta x only, now this is delta x minus a. So the function then is 0 everywhere except x equals a. This is the standard form. And it's equal to infinity at x equals a. And the same is true again. If you integrate this delta over all range possible value x, you get 1. Now if you multiply f of x times delta x, then it is equal to the function at x equals a. Then if you integrate it in this way, the integral then just gives you the value of x f equals a. That is important for you to realize that that's the case. So this is the standard way that I want you to think about the delta function. Suppose you had delta of x plus b, then that would be delta of x minus a minus b, because that negative sign has to be in there for it to be in its standard form. So I'm going to go here now in a moment and do one integral. Suppose you had to do this integral here as the author's expression to you. The integral from 0 to 3. Now, if this value where the function is going to be evaluated is outside of the range of integration, the integrand is 0. However, if this value is within the range of integration, it is just this results right here. So the range of integration is from 0 to 3. 2 is within the range from 0 to 3. Therefore, the integral of this entire expression is equal to 2 raised to the third power, or 2 cubed. So that's how you get 2 cubed, and it's equal to 8. One other thing I want to say, and then I'll do a couple of problems, is be aware of this situation here. Delta of some constant of x times x equals 1 over the magnitude of k times delta x. So you can use this identity from some problems that you will have. Okay, let's try out this now. So what I've given you as some homework problem is some regular Riemann integrals, and then I also have some mixed in with the delta function. So this is straightforward here, power law integration. The integral from -2 to 6 of 6x squared minus 2x minus 5 dx. This is just an arbitrary function that I chose. And then so everyone in this class know how to complete this integration. You go through the integration of a sum is the sum of the integrals. So the integral of 6x squared is 6x cubed over 3. And the same follows for those two values. And so you get that the final value then is 364. All right. What about this integral here? Notice then it's the product of the quantity 6x squared minus 2x minus 5 times the delta function that's written in its standard form. The only question you have to ask yourself now is this value within the range of integration? Yes or no? If it's yes, then the results of the integral is this function evaluated at x equals 5. So right here, I go and put that result. So the results of this integration is 6 times 5 squared minus 2 times 5 minus 5, and complete the expression to get a final answer. What do I have there? 135. Sorry for my print. Look at this here. The integral from 0 to 3 of x cubed dx. Look at this expression here, and you get this is that. Now suppose you have this expression. All right. Now this delta is not in its standard form. So you have to write this as delta x minus a -2. But -2 then is not within the range of integration from 0 to 3. That kills everything. The result of that integral there is 0. All right. See, so this has to be written in its standard form. Standard form is delta of the variable minus whatever place you're going to evaluate the integral. And here it has to be a -2, -2. All right, let's look at this one now. What is this integral here? Okay, so it's no problem. This is a standard Riemann integration. The integration of the cosine of x dx is the sine of x integrated from 0 to 2 pi. And the sine of 2 pi is 0, the sine of 0 is 0, you get 0. What about this integral here though now? There is the delta function, and it's a product. So the whole integrand then is the cosine of x delta minus pi over 2 dx. Is pi over 2 within the range of integration? Yes, it is. So the result of the integral is to evaluate this function, cosine of x, at one point, pi over 2. And the cosine of pi over 2 is 0. Notice that you get the same answer, 0 here and 0 there, but for entirely different reasons. All right, that's what I wanted to do. I wanted to illustrate a little bit about solving these integrations with the delta function being present when the delta function is not present. And just realize that the delta function is this oddness but it's needed in physics, because we often have a case like point charges where the density of the charge is located at one specific point, which is where that single point charge will be. So you will find delta function used a great deal in electricity and magnetism, which is where I've taken this information from my E&M book. It is used extremely often as well in quantum mechanics. Okay, all right, that takes me to the end of this now. So use this illustration and work through your homework problems. Okay, have a good day.